algebra. I've written the definition here again in case you forgot. So factorization algebra on some coset of opens in our topological space is an algebra for this operad that we built out of this set of opens, such that the underlying functor has this right quotient condition, and then we have this multiplicativity condition, which basically says that the value on some disjoint union of opens you want to UN is just a tensor product of individual values. And so the first lecture for today, I will be talking about some basic tools and constructions you can do with factorization algebras. So this is still going to be very general, and then starting from the next lecture, we will put much more restricted conditions on our space X. But for now, this is all still very general abstract stuff, and I will just be showing you some basic results that are very useful for working with factorization algebras. Okay, so the first thing we have are some factorialities. In X. So basically the question is what happens if we change the topological space. And there are two basic factorialities. So one of them says that if we have an open embedding, let's call it I. Then of course we get an embedding from opens of X into opens on Y. And in particular, we will get an embedding on the underlying operads, on the corresponding operads. And then, since taking algebras out of an operad is contravariant, one gets a functor from algebras for open Y to algebras for openness on S. So this is what we call restriction. This is so far from pre-factorization algebras. And then the other thing you can do is if you have a map the other direction, and now this is just any map, continuous of course, then I mean, by what it means to be continuous, a continuous map by definition exactly means that you have an induced map the other direction by taking pre-images, and then therefore, since pre-images also are compatible with disjoint decompositions, I can put a tensor product on both sides, and then for the same reason, by taking algebras, it's contravariant again. And so for the same reason, I again get a functor like this, which so I have either, I'm going to write this slightly abusively, I either have I upper star or F lower star. F lower star. So one of them is called, this is called restriction, and this is called restriction or pullback, and this is push forward. And in fact, one can then check, so this is now on pre-factorization algebras, but then it's an easy exercise to check that in fact, both of these factorialities restrict to factorization algebra. So both I upper star and F lower star preserve, even separately, the multiplicativity plus the vice condition, and therefore we get an induced factorization algebra on Y mapping to factorization algebras on X, which I will denote with the same name. I upper star or F lower star. Okay, let me give you one simple example where this can be useful. I will just do a sample computation just to get our hands on how these things work. So there is sorry, let A be an associative algebra. or a one algebra, then I will just claim it for now, but we will justify it a little bit later. So there is a factorization algebra on the sphere, on the circle, which is given as follows. It's just given by saying, I'm just going to tell you what it does on small intervals, and then you're saying, okay, the value at every interval is A. And it's just an extension of the one I had before, just that instead of just having a real line, I can close it up. And the structure is defined in a very similar way, where whenever I have two or some number of intervals, which are contained in some bigger interval, then from the perspective of this interval, I can somehow forget about this part. And since, let's say, I choose an orientation on my circle, then this orientation tells me in which order I'm supposed to multiply my elements of my algebra. And so the structure map here of the operad will just be the multiplication. So there is such a factorization algebra. And now the question we could ask, can we use the techniques we have learned so far to compute the value, well, let's call this factorization algebra A, and then the question is, can we compute the values on the whole sphere, on the whole circle? And one can sort of try to do this directly by choosing some clever Weiss cover, but in this case, there's a much easier argument to reduce it to something we already know, which is we can take the following map. So we have S1, and we can just do a stupid projection down to R. And then, so this will go here, this will go here. And now, so we do push forward along this projection. So we have A here, and then we will get a push forward factorization algebra here. And by definition, the value of this on S1 will be the same as the value of this on the whole of R, because the value of this on R is by definition just the value of this on the pre-method R, which is all of S1. And so now the only question is, what is this? And we already know how to compute, at least if it's of the example we saw, of the shape of the example we saw last time, we know how to compute this thing. So we just have to quickly observe how the factorization algebra looks down here. And so if we look at an open that's somewhere here in the middle, then we see that the pre-image is actually 2 copies of A. But in fact, if you look at a little bit more specifically, since the orientation here goes like this and here goes like this, you see that on this copy of A, if you have like multiple of them in a row, you will have the original multiplication of A. You could say this one is oriented this way. But up here, there's a reversal of orientation. So really, what you see that the value on such an open is A tensor A of as an algebra. And then if you look at what the value is at these special points, here you see you just have an open that's of this form, so it's really just A. And then here you also just have A. And outside here you have nothing, so there's the empty, and the empty just goes to the monoidal unit. And so from this, you see that using the computation we did last time, we already computed what this is whenever we have an algebra here, and then 2 algebras here and bimodules, then we computed that this is just the relative tensor product. Of course, I could put these ones here, but they don't contribute anything. And this is functional homology of F. Okay. So this is one easy way where the push forward shows up in practice. Okay.
Sorry, can you also get the bar construction, the cyclic bar construction description?
Yeah, you can. I think if you sort of choose a suitable Weiss cover where you allow to take out all possible compacts of this, then I think you can show that localizes to the cyclic category, and then you see that. Yeah, I don't remember exact computation, but I think you can Instead of doing it like this, you can directly choose something on the circle, which gives you the cyclic bar construction. But somehow this is a bit easier to explain because it just reduces to something I already showed last time.
But also you get like a geometric proof of this.
Yes, that's right. That's right. Yes. If you, of course, we're assuming that this factorization algebra exists, which now is just a circuit, but if you somehow construct it, which we will be able to do a bit later with methods of such. Okay. So this is the topic of functoriality, which I just wanted to mention these two things. Of course, they compose nicely. That's just because these induced maps on the operads compose. And yeah, and so now I will talk about two other important tools for work. Yes?
When you say they compose nicely, does this give me some kind of function out of a span category?
No. Sorry, what I meant, the claim I made was like very weak. I just said each individually composes nicely. And I expect there should be some sort of like both at once with some, but I honestly don't know exactly what the status of this is. And in fact, this is something I am interested in exploring in the future. Yeah, this is a very good question, and there should be a good answer to it. But so far, I'm just going to do a very naive thing, just state it separately. Yes. Okay. So the next thing I want to talk about is the topic of extension from bases. So maybe you know this for sheaves, that at least for ordinary sheaves, if you want to specify the value of a sheaf, it's enough to do it on the basis of the topology. And something similar is true for factorization algebras, which is also how you would maybe build this thing to begin with. But one has to be a little bit more careful about what type of basis one allows. So you can't just take any old basis. You need to have some basis with some special properties. So let me give you some definitions. So we fix, as usual, our poset in which everything takes place. And then we say a sub-poset B. And again, I will use both curly and straight letters. So I will try to make the curly one with a very nice bow at the end so you can distinguish it. It's called a multiplicative basis. If it satisfies two conditions. So first of all, it needs to be a basis, which just means that whenever I have any open in my U, and I have any point of that open, and in fact, not just any open in U, but even some open that's smaller than something that's contained in U. So remember, this down arrow just means I also allow things that don't live themselves in U, but are just contained in something in U. Then there has to be a B in B, which contains this and lives in U. It's just a usual basis condition. And now the multiplicativity condition it's basically saying that it's closed under disjoint unions, except we don't require it to be closed under all disjoint unions, but only under those that are subordinate to U. So let me write what that means. So let's say you have two opens in your basis such that they are disjoint. That's what this symbol means. And after a union, it's still contained in the down arrow view. So it's still contained, both of these together are still contained in some U that lives here. Then also we require that this disjoint union lives in B. Okay. And then often one needs one more condition. So it is if additionally we have that B is closed under intersections. So remember, this just is obtained from this by adding all finite intersections. So this just means closed under finite intersections. Then we say that B is a factorizing basis. And let me give you the key example to keep in mind that will be very relevant starting from the next talk, but I want to already show it here. So assume that X is some sort of manifold. Later we'll be looking at stratified manifolds too, but for now let's just think of ordinary manifolds. Then one choice you could make is you could say you let B be the set of embedded multidisks in X. So a multidisk, this just means that U is abstractly isomorphic to some disjoint union of our n. So let's say this is an n manifold. And if you look at this, then it's clearly closed under disjoint union because by definition we've closed under disjoint union by not just allowing this but multidisks. And it's obviously a basis. That's what it means to be a manifold, essentially. So that means that this is multiplicative basis. But crucially, and this is going to be a bit of an annoyance later, this is definitely not a factorizing basis. Because if you take the intersection of two embedded disks, it's in general not an embedded disk or even an embedded multidisk. But you can remedy this in some situations, like sometimes you can choose some collection of good disks. So by this I mean the basis of disks closed under intersection. And then if you can do this, you will get a factorizing basis. And for ordinary manifolds, this always exists. And I will say a little bit more about this later. Yeah, but this is really the prototypical example you should keep in mind for all of what I'm going to say next. This is really the mother of all factorizing bases. And so here's the key fact about why these factorizing bases play a role. And then using this key fact, there's a bunch of stuff one can very easily prove. So let me just state it. So if you have a multiplicative basis, and let's say you have a vice cover in U, then the upshot is that if you take U and you look at those things that are subordinate to your original vice cover, but only exist in your basis, then this is a vice hypercover of U. And if B is even factorizing, which means that B is intersection closed, Then, of course, this whole thing will be intersection closed. So that means this whole thing is not just a vice cover, but it's what I call the vice pre-sieve. And not just a vice hypercover, but a vice pre-sieve, which just meant it's a vice cover closed under intersections. And if you recall, these were exactly the ones for which we had the vice hypersheaf condition. Hyperdescent. So vice hyperdescent exactly tells you that the value here will be the co-limit of these for all of them. And the reason we care about factorizing bases is because we usually don't want hyperdescent, but only ordinary vice descent. And there, remember I had this little observation that there you really cannot do it for all these vice hypercovers, but only those which are close on intersections, which is why this condition is so important. Okay. And now, using this key fact, it's not hard to show the following proposition. I will sketch maybe one of the directions. So here's the statement. So let's say we have U, and let's for simplicity assume that U is closed under intersections. One can also say something if it isn't, but it gets a little bit more annoying to say. So for simplicity, I will just do it like this. And let's say we have a factorizing base. And often for U, we only care about taking all opens, for example, or like something that's very much in that spirit. So the fact that we have this restriction here is really not so problematic, but here it's really important that we have a factorizing basis and not just a multiplicative basis. Then we can show the following two things. So the first says that if you have a vice co-sheaf on the big thing, then first of all, if you restrict it to the small thing, it's still a vice co-sheaf. This is almost tautological, but the important thing is that A itself will in fact be automatically can extended from this restriction. So it will be the left hand extension from B back up to U from its restriction to this.
And these are just statements about like functors.
So yeah, exactly. Because as I was mentioning before, the vice condition for factorization algebras is just a statement about functors. And in a moment, I will also tell an operatic version of this, but for now, this is all just about co-sheaves or functors. I think I did. Somebody switched the board from behind it because I forgot. Yes. So this is one statement, and then there's some sort of converse, which says that conversely, let's say we have some vice co-sheaf on the small thing. Then you can try to ask yourself what happens if you extend it back up. And the answer is that, so this is now a pre-co-sheaf on U, and this is now again a vice co-sheaf. Okay. Let me see how I'm doing with time. Yes. So I think I will just give one, like just a proof of one of the statements, just to see. So this proof is not very hard. Like you can just, it's basically computing some co-limits. So let me just show you, for example, let's just prove 1b, just to see where the condition comes in. So here we're trying to show that A is a left-hand extension from its restriction to B. So what we need to show is that, let's say we have some U in U, we need to show that A of U, so we want to show that this is an equivalence from the co-limit of A restricted to the slice of B over U. This notation is now a little bit confusing because over U really means smaller than U in the poset. So I will write it in the notation I've been using so far, which is it needs to lie both in B and under U. And now you see that basically, so by this key fact, this thing is a vice cover, but in fact even a vice precede of U. And so this is just an instance of the vice condition. But you see that here we really need to assume that our B is close to the intersection, otherwise this argument doesn't work. And yeah, the other direction is a little bit harder, but you can do also arguments like this. Somehow, once you have this key fact, basically this key fact tells you that whenever you have a factorizing basis, it produces a lot of vice covers for you, or a lot of vice species for you. And then you can do some computations. Okay. And then, of course, from this, there's an immediate corollary, which is the thing we actually care about. Or not quite the thing we actually care about, but the limited version of the thing we actually care about. Which says under the same assumptions, so again, poset close to an intersection and a factorizing basis. Then we have functors from U to C, and then functors from B to C, and then here we have the restriction pan extension adjunction. And if you read what those two statements say, basically they exactly amount to saying that if you restrict on both sides to the vice co-sheaves, then this becomes an equivalence. Okay. And at this point, let me also make a remark. So one can attempt to drop this extra factorizing condition, so to drop the condition that these intersections close, because one really would like to drop this, because the examples we want are exactly just all this, and this just doesn't satisfy it, and so that's a major headache. So one can attempt to drop this additional condition, and you can almost do this by, instead of working with ordinary vice things, by working with vice hypersheets. And if you do that, you can still prove 1A plus B. This will still work. But I don't know about 2. So at least the direct proof, the one you get, the one that I didn't explain, doesn't seem to generalize. But maybe there's a more sophisticated argument one can do, and if somebody has any ideas, I would be happy to hear this. Because basically, this is the only obstruction I know to just fully working with hypercosheaves. Like, hypercosheaves are technically much more convenient to hypersheaves everywhere, except that this one thing we didn't manage to make it work. So if somebody knows some idea of getting this one step to work, it would be a way to make the whole theory much nicer. Okay.
So is it true that if I have a multiplicative basis that contains a factorization basis,
yes,
then the restriction is fine?
Yeah, then exactly. So I think as soon as I will say this later, where basically if there exists a factorization basis, which then you can always do stuff. Later we will basically bake this into our assumptions. I will say this, but this is somehow to deal with the case, or because in general we don't know if this even exists factorizing basis with of the type we care about. So now we still need to talk. So this was still about functors, so about co-sheaves. But what we of course really care about are the factorization algebras. And for this, we have to recall something that Rune taught us. And so this is the topic of operatic left-hand extensions. And so I will just recall one version which he explained this to us, which is that if you have any functor of operads, then you have that algebras, O algebras, and P algebras, but then the restriction functor has a left adjoint. And there's one more fact I need here, which I don't know. I don't remember if Rune mentioned this explicitly, but it follows by just looking at the pointwise formula. We need two more things. So the first thing we need is that when f is fully faithful, then so is this. Then so is this time extension. And in fact, in our setting, these will always be some poset of opens, and this will just be included in here as a full subposet with the same operand structure. So this will always be full faithful, and we need that then this will just be included as a full subcategory here. And then we need one more thing, which is a little bit special about, so this is still fully general about all infinity-operads. Probably should say infinity-operads. But there is one thing that's very special about the operads in R that appear in this talk, which is something you don't usually see for general operads. And that makes this operatic time extension work even nicer. And that's the next statement I need to quickly mention. So assume that this map from P to Q, let's even assume that's fully faithful. So I can assume that this is fully faithful and satisfies the following condition. I'll just call it star. So it satisfies the condition that whenever you have an active map, and I will in a moment translate what this means in our case and why it's usually true. So whenever you have an active map from some, this is F, you have an active map from some F of some tuple. I will denote the tuple by just overlining it. And whenever you have an active map to something in Q, let's say over M1, then there always exists a factorization where you first factor this by f of some co-Cartesian arrow, and then this is now just an arrow in the fiber. So this will be over this, and this is the unique active map. So of course, if and this thing will be right, and this thing has to be co-Cartesian both in P and in P. Yeah. So basically, this tells you that in general, of course, this is just an operad. So if you just have an object P bar, there might not be a co-Cartesian lift. But if your object already comes with a morphism to something, with an active morphism to something, then this co-Cartesian lift exists. And let me now just quickly explain what this means in our situation. E.g., so if you have a subset B of U like there, then the typical situation where this happens is if, so let's say you have B1, B2, and you have an operation into some U. then by definition, the existence of such an operation means that B1 and B2 are disjoint, and they both are contained in U. And so assuming that B is closed under such disjoint unions, subordinate to U, you will really have this object B1, B2 will exist in B, and you will therefore have this factorization. And so you see that if you have this with this condition, with this multiplicativity condition there, then this is always satisfied. Yeah, so this is a special property you can ask about a map of operads, and it's sort of for whenever you have a factorizing basis or even a multiplicative basis, this will always be satisfied. And now, using the pointwise formulas for operatic time extensions, you can prove the following lemma, which makes it much easier to work with these time extensions, which is the following. So you have, so assuming okay, yeah, I'll just write it again, assuming EQ is fully faithful and satisfies the star condition, then you have the following. So on the one hand, you have algebras for O and P, and then you have the underlying functors. And then, of course, if you take restriction everywhere, and then this commutes. But now, in general, so now you have adjoints here. So here you have the ordinary time extension, and then here you have the operatic time extension. So let me just start. This is ordinary time extension, and this is operatic time extension. And in general, this associated square, this mate square, it will not commute, but in general, there will be a 2 cell in this square. But the claim is that under this condition, the Lax square Lax or Lax, I don't know, of the convention, but anyway, this square, it commutes. And in fact, it is even a pullback. So being a pullback tells you that, so we know that this is fully faithful. So this thing is just some full subcategory of this. And being a pullback tells you that if you want to check if a prefactorization algebra lands in this image, the only thing you have to do is check whether the underlying functor lies in this image, which means you only have to check the ordinary time extension condition, and then it will be automatically operatically time extended. That's what this is saying. Okay. And as an immediate corollary, we get, so here, remember, we had the statement that the ordinary time extension, it restricts to an equivalence between bisalgebras here and bisalgebras here. And therefore, as a corollary, we get the first comparison result. So this is what's usually called extension from basis. Which says that, so it's the same assumptions as before, so U is closed on intersections, and D in U is a factorizing basis. Then this tells us that we have an equivalence between, so first of all, we have algebras for one operad, algebras for the other operad, and then we have this time extension, and if you put vice on both sides, then this tells us that the time extension restricts to the ordinary one, and then since we have an equivalence there, we will in fact have an equivalence here, and moreover, which restricts to, so you can just impose the multiplicativity condition separately on both sides, and then you can see that this equivalence preserves the multiplicativity on both sides, and therefore yields an equivalence between factorization algebras on U and factorization algebras on D. And this is somehow the main upshot of this whole section, that a factorization algebra on this bigger coset, for example, all opens, that's the typical use case. You can just give it equivalently, but just specifying its value on a factorizing basis. That's somehow, if you take anything away from the last 20 minutes, then it's like this equivalency. Okay. Yeah, I will skip the proof of this restrict. This is like a relatively easy computation. You just have to show that the multiplicativity condition is preserved. I think I should have done time for this. And yeah, so for example, this also justifies the thing I wrote, it's still on board. So I just claimed there's like a factorization algebra like this. And basically what I did is I just gave you the value on such disks. And there is a factorizing basis on the circle by just taking disks that are like small enough, like as long as they don't wrap around too much around the circle. If you have just small intervals, if you intersect them with each other, their intersection is still an interval. So it's factorizing. And so that means it's enough to give the value on those. Okay. Any questions about this construction? Does not seem to be the case. Okay, so then I will show the other basic construction one can do with factorization algebra. So first I will do it. Let's see. Probably I should start here. Yeah, so today I will just be introducing a couple of these tools. And then in the last lecture, we will actually use them to prove some Bloom statements there. And so yeah, maybe you will have to wait until then to really see all this in action. So the last construction for today is the one about disjoint union completion. So what do I let me just write this? So if you look at the definition of factorization algebra, there's a little bit of a redundancy in it, where it's still there, where somehow you have this in the coset of opens, you have disks, but you also have a bunch of disjoint unions of this, and then the multiplicativity condition basically tells you that the value on all those disjoint unions is just the tensor product of the value of the thing you already had. And so it might be reasonable to believe that you could just get rid of this extra multiplicativity condition if you just get rid of all these multidisks, because the value on the multidisk is already determined by the value on, or like the value on like something that decomposes as a disjoint union is already determined as the value on the individual pieces. And so it might be simpler to just have the data on the individual pieces. And so this is what I will explain now. So basically the idea is we can somehow get rid of multiplicativity by only considering connected openings, let's say. Connected with non-end. So this is just a bit informal, but I will now explain what I mean by this. So let me first I need a definition, which is one more property that a poset can have. And I'm sorry for introducing all of these words, which are then often a bit hard to remember, but I will try to recall them whenever I use them. So a subposet B is called decomposable if So it says that whenever you have something in B that decomposes as a disjoint union of two smaller things, and such that this disjoint composition is non-trivial, so both of these pieces are non-empty, then you want decomposable means that then you can do this decomposition within D already. So that this just says that U1 and U2 are then both already contained in D. And with this definition, we have the following theorem, which says that we have an equivalence. So for decomposable B, and maybe I should again say an example. Of course, if you do the thing I wrote before, where you take B, maybe I should say this first, example, if you take B to be like a multidisc, then this is somehow trivially decomposable, because by definition, it contains a multidiscs, but then when you decompose a multidisc into discs, they are all in there still. This is like a trivial thing. And the claim is that whenever you have a decomposable B, you can look at algebras on, let me write it like this, we can look at algebras, multiplicative algebras on B tensor. So yeah, I think I had this notation, but I will remind you again. This just means multiplicative prefactorization algebras. So it's algebra for this operator with the multiplicativity condition. And the category doesn't change if you take B and you close it under disjoint units. So I had this already in the board last time, but let me just remind you, this is obtained from B by taking all possible disjoint unions that exist in B. Close B under disjoint units. In particular, just to spell this out explicitly, in particular, this means that the empty set is in here because it's the empty disjoint union. It's like the disjoint union of nothing in B. In particular. And so what this is telling you is that if you have some B, which then the multiplicative algebras on the B are the same as the multiplicative algebras after you throw in a bunch of all the possible disjoint unions. So I will not give a proof of this theorem. I will only illustrate one specific case somehow, which is the Nollery one. And then, yeah, the proof of this, I'm sorry, I didn't say what the equivalence is. Equivalence is given by the operatic extension. So here we just have restriction, and here you have operatic left-hand extension from this operad to this operad. So you have the adjunction, and then you just have to do a bunch of computation, which are not like super trivial, but one can do them to show that this really is an equivalence. But rather than try to go into the proof of this, I will just make a very trivial example of what's happening. I think that will be a little bit more illustrative. So, example. So this is about the role of the empty set. Okay. So observe that if you have a B, so let's say we have B decomposable, and let's say B contains already the empty set. And then you might wonder what happens if you remove the empty set. So then, if you add in all disjoint unions here, you will get the same as if you add all disjoint unions here. And so by the theorem, you will see that this is literally the same. And so therefore, algebra, okay. And therefore, by the theorem, algebras on B without the empty are the same as multiplicative algebras just on B. Because both of them, they are compared to their disjoint union completion, it's the same. Sorry, I'm missing B here. And I want to explain this in a little bit more down to earth. So let's explain this. Explain what this means. So already last time, I made a very trivial observation, which I will repeat. So if you look at just the empty set inside B and the operand generated by it, then we already saw that this is just the commutative operand. Because it has one object, and then whenever we have a bunch of copies of the empty set, they all disjointly embed into the empty set somehow. So this is just com. And so what this means that if you are given any prefactorization algebra on B, then in particular you can evaluate on the empty set, and this will be a commutative algebra. But in fact, because we can just restrict it to this copy of the commutative operand that sits inside here, but in fact you can say a little bit more. Moreover, you can say that since you have inclusion, so whenever you have a B in curly B, you always have an inclusion from empty, union, empty, and a bunch of copies of empty, and then one single copy of B. All of this, of course, disjointly includes into B. And so from the structure map of this, you will get that A of empty, this is a commutative algebra. And here, of course, I wrote them in this order, but there's no real order here. So this commutative algebra acts on A of B, where this is the use map from this inclusion is the action map. We have A of empty of empty of empty, tensor A of B maps to A of B, and that's the action map. And so you see that every value of the factorization algebra is an action for this commutative algebra. And now, if you look at the multiplicative case, so in the multiplicative case, the multiplicativity condition exactly says that A of empty needs to be the monoidal unit, and this will have its trivial algebra structure. And all these actions will also be true. And I mean, this is not the actual proof. The actual proof is actually not very hard. It's just a very short time extension computation. But I think this is a much more understandable way of explaining what's happening rather than just doing a computation, which is that this is saying that the data of the empty set really consists of this commutative algebra plus all these actions, but in the multiplicative case, all this data is true. So in the multiplicative case, all this data is true. And that's what then explains this sort of baby case of the theorem. Okay. Yes, so then there's one last corollary. Which is the thing I started with in this section, but I didn't state it yet as such. And again, maybe that's the thing to take away with. The corollary says that if B consists if B is decomposable, actually, if this will be trivial, sorry. If B consists only of connected and non-empty opens, then of course, algebras, multiplicative algebras on the disjoint union completion. So these, by the theorem, are the same as multiplicative algebras on B. But this assumption, the fact that all the things are connected and non-empty, means that there's no non-trivial instance of the multiplicativity condition appearing, because there's no non-trivial decomposition, which means that this n, I can just get rid of it. And of course, the example you should think about, where B is the category of contractible disks, so like actual disks, disks in X, and then when we take the disjoint union completion, this will be what I will write disks. So there's an extra X here, S here. So these are just disks, and these are multi-disks. Okay. And then in the last few minutes of today, I'm basically at the end. The only thing I want to mention is that now you might be very curious, because it seems like I didn't finish the story, right? So here, in the first thing, at the very end, we got something about factorization algebras, but now we only have something about multiplicative algebras. And so the question is, you might wonder, what happens if we put the vice condition on both sides? And actually, this turns out to be more subtle than one would really believe. And in fact, the answer is that I don't know the answer. So I do not know if this equivalence restricts to an equivalence on actual factorization algebras. So and the problem is the vice condition. So let me, in fact, one can boil down the difficulty to the following question. And again, this is one of those places where if somebody has any ideas, I mean, I'm going to write it and you're going to laugh because it seems such a innocuous question, and I'm sure somebody will come up with a super trivial counterexample or something, but at least we didn't see it. So the question is, given a multiplicative algebra, a multiplicative prefactorization algebra, A, on something that is two disjoint topological spaces, such that if you restrict it to each of the two things, it's vice. And then the question is whether the A itself is already vice quotient. And every time I look at this, I think this can't be so hard. Like surely there's either a very easy proof or a very trivial counterexample. And if somebody sees it, please let me know, because this has been annoying me for a long time. Okay, I think I will stop here, and I will see you all after the next session. Questions? Yes.
Examples for places where you don't have the factorization basis. Do you have an example? Or
Okay, so I should be more precise. Of course, you can just, of course, they're like trivial base. You just take the basis of all kinds of like something stupid like this. But the thing I was referring to is the following, that this is already going towards the topic of the next lecture, but when you have a manifold, let's say smooth, then you would like to say that you take all the disks in N. And you look at this and it's not a factorizing basis, but then it is actually like it's a true statement that for smooth manifolds, one can pick a basis like this as factorizing. Yeah, they're small enough and like some convex with respect to some metric or something, like there's some tricks like this. But next lecture, I will start to talk about stratified manifolds. And I have no idea whether the same statement is true there. Like in the ones you can write down, it's always, you can sort of write down the basis by hand, but I have no idea if one can prove in general that such. Basically, the statement is I don't just want a factorizing basis that's like random, but I want one that's made out of this, basically. Or this stratified this when I have stratified spaces. And there's always a multiplicative basis, which just consists of all multidisks. And then the question is, does there exist a sub-basis that's factorized? Yeah. Yes.
In the remark up there where you say you don't know whether it's an equivalence, so it is like, it follows from this that it's fully faithful, and the question is it essentially subjective? Is that?
Yeah, one direction is clear, yeah. Like
I can restrict to full subcategories there.
Exactly, restrict to full subcategories. Yeah, basically the statement, it really boils down to an instance of this, where you have something, you have a multiplicative basis on the big thing, which is vice on the small thing, and you want to know whether it's also vice on the big thing. And by some very easy computations, you can actually reduce it to this like one specific question, where all you want to know is whether you have an algebra and a disjoint union that's vice on each of the two pieces, and you need to know whether it's vice in total. And somehow it seems like it shouldn't be so hard.
So do you know this if I take a manifold and I take multi-disks and disks?
No, even there I don't think I know. But again, this is one of those things where, yeah, maybe there one can look up something with. But yeah, I don't know enough about differential geometry to do any sort of non-trivial arguments. So like all of these are all arguments you can do just very generically by knowing very little inputs. So yeah, maybe there is some good arguments for this.